Yes, so if there is any doubt regarding memory elements lectures, how many of you have actually seen the lecture videos? I don't know, I have not seen the number of views in the videos, but no one has asked any offline questions also. So I don't know really if you are seeing the videos or not. And there are a few points which has to be understood a bit more carefully in that part actually.
Sir,
Hmm. Yeah.
sir, can you please explain how to calculate the propagation delay time?
Propagation delay
Means,
time will be given to you because
uh,
the gate delay you know. So what is the gate delay, or what is the delay of a particular block? Like, yeah, I hope you are trying to understand in terms of the ripple adder, right?
yes, sir.
So there either you will be given the gate delay. So gate delay means delay at a particular gate, the AND gate, the OR gate. Okay. And or otherwise you will be given the delay of a full adder or a half adder, the total delay in a full adder. So if the total delay in a full adder is given, then so many full adders are connected in cascade. So the final delay will be that much times multiplied. If you are given the gate delay, then you have to note how many your how many levels, how many gate levels are there in a particular full adder. So in a full adder, I guess there are two gate levels in order that the carry is generated. So if a gate delay is given, multiplied by 2 is the delay of the full adder, only of one full adder block. Now as many full adders are there in the circuit, that many times the that delay would be multiplied, the full adder delay will be multiplied to get the total propagation delay of the ripple adder. So something you have to know something at the very start, either the gate delay or the block delay. Some information would be given to you.
Sir, in tutorial, like there was a question on that uh, look ahead adder, and we have given the propagation delay time of OR gate, AND gate, and uh, NAND gate and NOR gate,
Hmm.
and we have to tell the propagation delay time of look ahead carry adder for 4 bits.
Hmm.
So then how to calculate it? Means for the input we have that complemented and both uncomplemented form.
Hmm. So there in the look ahead carry adder, there is this block whose delay will always be same, uh, because it is looking ahead, it is calculating the carries beforehand. So that block which is calculating the carries beforehand has a particular number of levels of gate levels. I hope you understand the levels of gates. So first the AND operation, then the OR operation, so there are various levels. So I don't remember the circuit uh, actually in my mind right now, but that as many levels of gate are there in that block, the delay will be that much. However, there is an initial input you have to process, that I and Pi and Qi, right? So those things you have to calculate, then you have to supply to this block, and at the end of this block also you have to have a further processing so that you can get the sum bits. So I guess that requires one more gate level, and at the input side, to calculate this P and Q, I guess one or two gate levels are more needed. So by looking at the circuit you will understand. So when you draw the circuit, you have to
So
then
like
understand.
in the carry look ahead carry adder, uh, we use the two XOR gates at the input and when we are calculating the SIs.
Hmm.
So, but we don't have a XOR gate as given in the question. So we have to form a circuit of an AND or
And or.
NAND gate.
Hmm.
Means when we have calculated PIs and CIs, we don't have their complemented form. So we have to consider the propagation delay in calculating the complements also.
Yes. Yes.
Okay, sir.
Hmm.
So, in
Hmm.
lecture, when you were discussing about propagation delay,
Hmm.
there you said that you gave an example that if there is a propagation delay of 10 nanosecond for each full adder, and
Hmm.
there is a 4-bit word. So you
Hmm.
said the total delay would be 80 nanosecond. That is 10 multiplied by 4 multiplied by 2. So why you multiply it by 2? Because it's given for a full adder, not for a full one level.
Oh, is it so? Then it will be 40. So I have, if I have said so, then I have, I thought that it is a gate delay probably, because there are two gate levels in a full adder. So then I have thought that it is a gate delay. But if it is a full adder delay, then it will be 4 into 10. That is true.
And so one more thing, like in tutorial, there were some questions in which we were given BCD inputs.
Hmm.
So, in one question, we were given the minterms for corresponding to which will be having output 1. So,
Hmm.
while constructing the truth table, when we'll land in the input from 10 to 15, do we have to consider it as a don't care or just leave it?
So it depends on exactly how your problem is framed. So if your problem states very clearly that BCD inputs are only received, okay, that will mean that the invalid inputs are not there coming in the circuit. So only BCD inputs are getting received. Okay. Then in that state you can consider, since the invalid states are not coming at all to the input side, then you can consider that for those inputs output you can consider as don't care, because those inputs will never appear at the input side. That is that has been confirmed um, by the problem setter actually. But if it is like that, when BCD input comes, if I state like this, so when BCD input comes, then you should activate some outputs. That means apart from BCD inputs also other inputs can come. So it depends on the language of the problem actually. You have to read the language carefully in these cases. Okay. So if I say that when BCD input comes, then the output will be like this. That means there is a probability that other inputs can also come. The invalid BCD inputs can also come. In that case, for those you have to make the output strictly 0, because you don't want anything to come at the output in that case. However, if it is stated that only BCD inputs are received, or only BCD inputs are coming at the input of a circuit, that means other inputs are not even coming. So you can ignore those, or you can make them don't cares in order to simplify the circuit.
And so one more thing, we are given a BCD to 10 line decoder. So
Hmm.
what does it mean? Like where does those five outputs, six outputs gone? Or like in
In
tutorial
in
also there were
हाँ हाँ बोलो पूरा बोलो.
in tutorial there was a question that we are given BCD to 10 line, and also in we in 7 segment decoder we also have seen for those digits. So where the rest of the outputs gone?
Where the rest of the outputs, acha, in these cases are like uh, outputs are only 10 in this case, because you would like to have any one of the 10 outputs activated when the input is some of this BCD codes. Okay, so this is the nature of the circuit you are trying to construct. So in that case it is BCD to 10, or what did you say, BCD to 10, or what is the name of the circuit that you said?
BCD to 10 line.
10 line, BCD to 10 line decoder. A BCD to 10 line decoder is, you have 10 outputs and any one of these outputs will be activated when the input is the corresponding BCD number. Okay, that is the thing.
But sir, decoder has a input like it is from n cross 2 to the power n. So corresponding to
That is a
3, 4
binary decoder. That is a binary decoder. So in binary decoder it is like that. If in a binary decoder, if you have n bit input, there would be 2 to the power of n number of outputs, because all the outputs will be covered in that case. This one is a BCD to 10 line decoder. Okay, so input side you will have a 4 bit binary word coming, output you have only 10 lines, 0 to 9. So when the input is 0 to 9, then you will have all these outputs, corresponding outputs going high. But when the input side will have some binary number which is not a BCD, then you have to restrict the output to 0, all of the outputs in this case.
Okay, sir. Thank you, sir.
So decoders can be, decoder means you are basically decoding something. So the idea is like that. So if you read the encoder part, you are encoding something. So this coding means, code means you are actually uh, going to a digital domain or coming out of a digital domain. So code is always in a digital domain. Okay. So encoding means there is something at the input side which may not be a digital thing, but at the output side you will get a digital word. So encoder is working in that manner. If you observe the working of the encoder, it is working in that manner. So whichever input is getting high at the encoder side, it is giving a number associated to it, a digital number. In other places, if you are working in some clubs or somewhere in IIT Roorkee, you might have come across encoders. Encoders are exactly that. It is sensing something, it is sensing, and then it is giving directly a digital output, a binary word it is giving. What is a decoder? Decoder is the exact opposite. In decoder, a binary word will be received and a output will be generated which corresponding to that binary word, which will identify that what is that binary word. It will identify what is that binary word. So in our digital electronics, the decoders that we are studying is doing exactly that. In other places also decoders are there where the exact value can also be given out. So here the corresponding pin is getting activated, but sometimes in other other decoders can be like that, where exactly the value will be coming out as an analog voltage. That much of analog voltage will come out. So this sort of operations can happen. These are the major principles of decoder and encoder. whereas we are studying it in the limitation of digital electronics, in the purview of digital electronics. Where both the input and the output side both will be like both will be in digital, basically both will be in 0 and 1.
Sir,
Hmm.
so if the question comes like design a combinational circuit, then we have to design it from the gates, or we can use decoders and coders in that also.
Normally you will have to design by gates. If decoders and marks, using decoders and marks, this sort of statement is not given, you should draw it with gates. You should like simplify the K-map or the McCluskey table and give the simplified combinational circuit. Okay, and in some questions you will be asked to design using decoders and marks. In those questions you have to use the decoder and marks.
So, sir,
In
like in tutorial,
let me finish. In practice you can always use decoders and marks. As you can see, it is very easy. In practice you can always do that, but for the purpose of exam we also would like to understand whether you can do the simplification of the circuit or make a combinational circuit using gates and all. So questions are normally given, two questions you will have normally. Actually this time midterm is not there, so I don't know how end term question I will frame, but normally in midterm we give one question is for with K-map reduction. So it is mentioned like design a combinational circuit for this particular problem. A problem is given. Another problem, another numerical is given where it is told that use decoders or use muxes, like that. So in that way you have to solve the questions. Yes, Saksham.
so like we were asked to draw the subtractor circuit in tutorial as well.
Hmm.
So there we need to draw the gates only, like we not with the block diagram or decoders, like those things.
No, we not with decoders, but there you can use the ripple adder because it is a very standard circuit. You can use the ripple adder there. Sometimes it is we allow, if you draw a smaller block, if you design a smaller block and using that you make the larger circuit. So we know that you know the smaller block configuration also, and using that you can make the larger circuit also. So that is perfectly fine. Okay. So you see that the subtractor circuit, you can actually draw up a truth table for the subtractor circuit and make a and do a K-map reduction. All these steps you can follow and give us a circuit, give a circuit. Okay. Another method is that you already know that there exists a 4-bit triple adder, and using that you can redesign it as a subtractor circuit, that you already know. But if when you are using that, you should also then like elaborate how the ripple adder is formed, how the adder is formed, and how you are using the adder as a subtractor. Okay. If it is already given that use a 4-bit ripple adder to make a subtractor circuit, then you don't need to show what is inside the ripple adder. But if it is only given that draw design a subtractor circuit, then if you are using a ripple adder, you should also clarify that you know what is a ripple adder, how it is doing the addition, and how you are converting that addition to the subtraction. So that is the case. So I try to make the because I know that there is a lot of flexibility actually in all these circuit designs and all. I try to frame the questions in such a way that you understand what exactly you have to do. But even in case you have any doubt, during examinations, I am always available there. You should ask me what is exactly to be done. I will not tell you the exact circuit, but you should, I will understand whether you have your approach is correct or not, and I will say that yes, you, in this way or in that way you can approach the problem. So this I always do, because I know that there is some there can arise some confusion in exactly what way you have to do it. But I try to make it as restricted as possible. Like I mentioned, whether you have to use um, decoders, or you have to use the ripple adder, or which whatever thing. Yeah, I also like ask you in this way that you draw up a particular, maybe the comparator for 2 bit, and use that to make a 4 bit. So you should understand then that you have to use the smaller block to make a larger circuit. So this sort of things will be mentioned in the problem. If nothing is mentioned, then that basically means you are free to do anything. If nothing is mentioned, okay. But in those cases, you should maybe it is better to ask me, because I may have something in mind. Then I would clarify to the entire class that do it in that manner. Okay. Anything else?
Sir, is memory elements the last module, or there is one or two or modules?
No, 2 more modules are there. I told you already that 3 weeks will be there. So this is the second week, and the next week also there will be some lecture videos given. After that, I hope there will be no other lecture videos. Okay.
Okay, sir.
And ma'am will start from the next week, I think. 12th. 12th she will start. So why today so less number of people have joined? What is the problem? Only 11, I think. 12. So why only 12 people are here?
Sir, maybe others don't have doubts.
So most of them are not having any doubts in any case. But at least I observe around 30 people are there. Today it is very drastically less. So is there any problem in the country happening in internet? There is Rajasthan people maybe not joining. I don't know, but others I'm not sure what has happened. They have not joined. Anyway, so if there is anything else, if there is nothing else, then I think we can end the session today. Hmm?
Sir,
Huh.
sir, for the next week's tutorial, please don't keep the deadline on 15th, because it's Diwali on that day.
Oh, acha. Okay, 15th is Diwali.
Yes,
Okay,
sir.
I can move it 1 week later. So it is only like ending the session. I will not have any further classes also. Okay.
Okay,
Okay.
sir.
Hmm. Hmm. If I accidentally I make it 15, you let me know. Okay. I can change the deadline even after posting
Okay,
the
sir.
assignment.
Okay,
Okay.
sir.
Okay then. So fine. So we can I think we can end the session since no more doubts are there. Okay. Okay. Thank you. Thank you for attending.